In 2025, Dennis Gaitsgory received a $3 million prize for a discovery that less than 15 people in the world can understand, but its effect ripples through the entire universe of mathematics. He solved a problem that had stood like a wall between the great continents of mathematics for decades. Along with his team, he published a proof that is so long and so dense that it crosses over 1,000 pages. They resolved the Geometric Langlands Conjecture. This is the story of a man who solved one of the biggest and long-standing problems in mathematics. People who follow the field say, this is the biggest breakthrough in a generation. By solving this mystery, he has changed the way we look at the fundamental building blocks of the universe. For a man who just won the $3 million Breakthrough Prize, the biggest cash award in the field of mathematics, Dennis Gaitsgory has spent a good portion of his life feeling like a prisoner. He grew up in the Soviet Union during a time when the borders were difficult to cross. He spent his youth in Soviet Central Asia and Chisinau, the capital of Moldova, believing he would never see the world beyond those fences. This sense of being trapped stayed with him long after he left. Even now, living in the freedom of Bonn, Germany, he admits he cannot satisfy the thirst for travel. He moves from country to country because for the first part of his life, he was told he could go nowhere. After he emigrated west, he simply could not satisfy the thirst for the knowledge that he could go to almost any country he chose. He wanted to see the world. The seeds of his breakthrough were sown during the COVID pandemic. It was 2020, and the world had stopped due to the pandemic restrictions. For a mathematician, this was a luxury. While other people fretted over the closing of shops and the silence of the streets, Gaitsgory used the quiet to hunt for a ghost that had haunted his field for decades. He was chasing the Geometric Langlands Conjecture. It is a problem so vast that it is often called the grand unified theory of mathematics. To solve it, Gaitsgory and 8 of his colleagues eventually published 5 research papers. Together, those papers totaled nearly 1,000 pages of dense, difficult logic. The work was colossal. It earned him the 2025 Breakthrough Prize in Mathematics. The prize citation praised his foundational efforts in proving this conjecture in characteristic 0. Even though the work is highly abstract, the consequences will ripple outward. It builds links to quantum physics and algebraic geometry. It is like the early success in the Langlands Program that led to the proof of Fermat's last theorem by Andrew Wiles in 1995. Gaitsgory's achievement is a once-in-a-generation advance that could reshape the mathematical world for decades.
The Breakthrough Prize in Mathematics goes to Dennis Gaitsgory.
Here's one piece of advice I'd like to share with people who are starting down this road. You don't have to walk this path alone. Find folks you find it fun to talk math with. Thank you.
To understand what Gaitsgory did, you have to go back 50 years. In 1967, Robert Langlands, a Canadian mathematician, proposed a revolutionary idea in a letter to André Weil, a fellow mathematician. Langlands suggested that seemingly unrelated areas of mathematics, specifically number theory, geometry, and analysis, were in fact connected, like secret twins. He believed a Rosetta Stone existed that could translate the language of one field into another. The Langlands Program, often described as an ambitious attempt to redraw the map of mathematics, is fundamentally a grand, unifying proposal for a mathematical translation theory. At its core, this theory posits a hidden foundational grammar that connects 2 seemingly disparate mathematical universes: the world of prime numbers, algebraic equations, and arithmetic geometry, with the world of smooth, elegant structures of analytic waves, complex functions, and representation theory. The program's vital engine is this proposed reciprocal correspondence, a kind of mathematical Rosetta Stone, which would allow mathematicians to convert deep, intractable problems from the number-theoretic domain into equivalent, potentially solvable problems in the analytic domain. This capability offers a powerful new strategy for tackling challenges previously deemed impossible within their original context, by leveraging the formidable tools of analysis, symmetry, and algebra from the wave side to unravel the mysteries of the whole numbers and algebraic structures on the prime side. The program has really grown since it started. It began in number fields, looking at rational numbers, which is the classical Langlands stuff, then expanded into an area known as Geometric Langlands. That second step actually connected it with modern theoretical physics. Now there's even a new, purely geometric version. In every case, though, the core idea is the same. It links things that capture symmetry with highly symmetric analytic or geometric objects. It's been key to some huge wins, like the proof of Fermat's last theorem, but realizing Robert Langlands' complete unified vision is still a monumental work in progress. Gaitsgory fell in love with a specific corner of this map. In the 1980s, thinkers like Vladimir Drinfeld and Alexander Beilinson started looking at a geometric version of the problem. They stopped looking at numbers and started looking at complex curves called Riemann surfaces. They wanted to see if they could replace simple functions with something richer called eigensheaves. Drinfeld and Beilinson realized that to make Langlands geometric, you must swap functions for these sheaves. They found a grain of sand, a concrete piece of the correspondence, by using ideas from quantum field theory and conformal field theory. Gaitsgory was just a student when he first heard Beilinson speak about it. He told Quanta magazine that he felt like a newly hatched duckling that had just seen its mother. He was imprinted. The beauty of the idea took hold of him and never let go. For the next 30 years, almost every hour of his working life was a step toward proving that this geometric version was true. He and his collaborators developed vast new machinery to prepare the ground. They used derived algebraic geometry and higher category theory. Only once did his massive textbooks even mention the word Langlands. He himself co-authored 2 massive textbooks laying the foundations of derived geometry. He was building the underpinnings for what came next.
I was born in Moldova. That time it was part of the Soviet Union. Then I partly grew up there and partly grew up in Tajikistan, which was also part of the Soviet Union.
Dennis was born in 1973. His father was an applied mathematician who liked to give the boy puzzles. But Dennis was never good at tricks. He told the Clay Mathematics Institute that he never had a knack for isolated, difficult problems. He did not care for puzzles that had a clever answer. He was one for the big ideas. By the age of 12, he and his father were reading math textbooks together. He said that by the time he entered university, he knew the basics. This thirst for the big picture showed itself early. He attended Tel Aviv University from 1990 to 1996 and found himself drawn to the mathematical theories he was being taught. He began to appreciate the real aesthetics of the subject. Something clicked when he enrolled in his first several classes. He started to derive great pleasure from carefully thinking through the theories. He found teachers like Joseph Bernstein who spoke with a clarity that Gaitsgory began to crave. He learned that math could be beautiful. Bernstein ran seminar-style courses at an advanced level. His teaching was notable for its depth and its light. Gaitsgory had to summon enough impertinence to ask a question every time he did not understand something. Aside from math, Gaitsgory is a man of wide interests. He has joked that mathematicians tend to deny themselves the simple pleasures of life while life passes by, but he does not always follow that rule. He bounces from one hobby to another. In recent years, he took up yoga and began studying Arabic. He even tried Argentine tango. He developed a passion for travel because of his childhood restrictions. Having grown up under Soviet limits and the conviction that he would be a lifetime prisoner, Gaitsgory now revels in the freedom to visit any country. He remarked that after moving west, he simply could not satisfy the thirst that he could go to almost any country that he chose. According to him, few things have been as rewarding as exploring the world. Despite his intense gaze, he is a quiet man. He enjoys talking about math with his friends, but has little patience for small talk. He told Scientific American that some people go to a bar and drink something. He and his colleagues have a bar at the Institute too, but they talk about math. They talk about soccer, and we talk about math. He once named sections of a draft paper after Star Wars episodes. It was an homage that had to be removed later. Some of his peers didn't find it that funny. He still managed to sneak in a line from Yoda in one of the chapter, "Fear will keep the local systems in line." His career took him from Israel to the United States. After finishing his doctorate in 1997, he spent 2 years at the Institute for Advanced Study in Princeton. He was a junior fellow at Harvard. He won a Clay Research Fellowship in 2000. This allowed him several years of independent research. He then took a job at the University of Chicago and became an associate professor by 2003. In 2005, he moved to Harvard as a full professor. He eventually became the Herschel Smith Professor of Mathematics. While he was there, he met a young mathematician like Sam Raskin, who would go on to become one of his biggest collaborators. In 2021, he returned to Europe. He accepted a director position at the Max Planck Institute for Mathematics in Bonn. His publications include numerous technical articles and multi-volume monographs. The breakthrough announcement marveled that he had dedicated 30 years to proving the Geometric Langlands Conjecture. It credited the decades of work by him and his friends as the foundation of the new proof. Before the breakthrough, the Geometric Langlands Conjecture in characteristic 0 was one of the great unsolved problems. In simple terms, characteristic 0 refers to a property of the underlying number system, called a field in mathematics, being used in the conjecture. A field has characteristic 0 if, when you start adding the number 1 to itself, you never get back to 0. Gaitsgory had proven parts of the conjecture over the years. In 2002, he, Edward Frenkel, and K. Valonen proved the conjecture for curves over finite fields. In 2004, he extended it to complex curves under some conditions. These results are now classics. They dealt with the function field version and certain parts of the geometric case. But they stopped short of the full statement. Experts continued to chip away at the edges for years. The problem was a technical nightmare. Gaitsgory and his friends formulated the best hope versions of the conjecture, often using tools from physics. By 2012, he and Dennis Gaitsgory had made the conjectures precise. He even outlined a strategy in 2013, but many steps remained unchecked. It was unclear how to prove that certain complicated geometric pieces did not vanish or cancel out. Until 2022, the world only knew that these pieces should be there. No proof was in hand. David Bensvie and others remarked that no Langlands result of such scope had been proved in the other settings. This made the geometry case even more daunting for everyone involved. The final key came from Sam Raskin and Joachim Fermi. In early 2022, they showed that a certain expected contribution is indeed non-zero. Gaitsgory told Quanta magazine that after their paper, he was certain they would do it within a short period of time. A technical hurdle was cleared. The white noise of the Poincaré sheaf truly contained all the signals of the eigensheaves. The geometric picture required this to be true. Once this was in place, Gaitsgory and his collaborators could piece together the remaining arguments. Langlands stood as a conjecture with outlines and partial proofs, but now the final steps were coming into view. The writing of the final argument was a remarkable story in itself. It brought together among 9 co-authors the best of the best in the field. It was like the Avengers of mathematics. Dennis mentioned to Scientific American how every day he was writing to this guy or that guy. Different parts were coming together. The pandemic emptied his travel schedule in 2020. He spent 3 months lying on his bed and just thinking about the problem. That intensive brainstorming led to a 6-author paper that planted the seeds for the final proof. He was finally closing in on the goal that had defined his life. By spring 2022, the group knew they had all the pieces. Gaitsgory went into high gear. He ended up writing about 95% of the text himself. He had a skiing accident that had him convalescing in bed. He asked himself what else was there to do. He recalls watching Star Wars with his young son while dictating large swaths of the argument. He had a bet with Sam Raskin. Gaitsgory promised him a bottle of scotch if the proof worked out. In lieu of champagne, they toasted with a good whiskey once it was clear the proof would hold up. The group finished writing by early 2023. They spent another year polishing the manuscripts. They finally posted all 5 papers on the internet in February 2024. Along the way, they constantly checked every argument. The proofs build on a framework so rich that it is difficult to believe there could be a mistake. The result is a set of interconnected papers. They developed whole worlds around the problem. They provided more than a solution, instead a wealth of new tools for future work. They built a new way of thinking. Even before solving the Geometric Langlands Conjecture, Gaitsgory's resume was stellar. He won the European Mathematical Society Prize in 2000. He was elected to the U.S. National Academy of Sciences in 2020. This is an honor held by only a few living mathematicians. The prize citation placed his achievement alongside the other great breakthroughs of the decade. Like many mathematicians, he keeps his private life out of the spotlight. He lives in Bonn and is married with children. He rarely discusses personal details in public. We know that his wife was by his side while he was writing the proof, and she knows the story of how it developed. But he admits he cannot describe the content of his work to her. He knows his family and friends cannot follow the math. The original dream is realized, but it is not the end of the story. Gaitsgory has likened the achievement to chipping off one piece of a big rock. He believes we are still far from the core of the truth. This massive result opens many new questions. People are asking about Langlands with punctures, or the version inspired by physics called quantum Langlands. They want to make effective and computable results from this work. These are the new frontiers that are now in view for the whole community. Colleagues are already turning to these challenges. Gaitsgory and Sam Raskin have begun translating their geometric proof into the function field setting of algebraic number theory. Quanta reports that they are making progress toward a more precise proof. Others are exploring the links to physics. The language of geometric Langlands connects to conformal field theory. Some hope these ideas will solve problems in quantum physics that have been stuck for years. Mathematician David Bensvie remarked that the fact that one of the major pieces has fallen should have repercussions throughout the correspondence. Number theorists and representation theorists are studying the new work for inspiration. The ideas will eventually seep through all the barriers between subjects. Brilliant mathematician Peter Schulze quipped that he is already many papers behind trying to understand the new proof. Meanwhile, Gaitsgory has won himself a bit more breathing room to think. Having spent 3 months lying on his bed and thinking, he is savoring the accomplishment even as he looks ahead. He will continue to explore Langlands and its cousins. These results are so robust and rich that once you get started, it is hard to stop. His 30-year journey has changed what we know about the mathematical world. It has unleashed a torrent of new directions.